This is the last video from Chapter 3. It's about balancing chemical equations. Balancing chemical equations are part of the law of conservation of mass, which, as you remember probably, says that mass can neither be created nor destroyed. So what does that have to do with balancing a chemical equation? Well, obviously, if you have the same number and type of atoms on each side of a chemical reaction, then you've maintained your mass. And that's really all the law of conservation of mass says. So just so you're familiar with the symbolism that chemists use, reactants, the things that you start with, lie to the left of the arrow. Products, the new things that are made in the chemical reaction, lie to the right of the arrow, and the arrow simply stands for yields or produces. Okay, so this is saying 2 iron atoms in solid form, so the phases are in parentheses, react with 3 molecules of diatomic chlorine, which is a gas under normal conditions, to produce 2 formula units. Remember, ionic compounds are called formula units and not molecules, of iron 3 chloride. Okay, so now we're getting into real chemistry. You need to know names and laws and other stuff. Here's a table summary of the things that I just went over. One thing that wasn't in the last reaction is AQ, which simply means that something it stands for aqueous, but what that means is something has been dissolved in water, that you have a solution. So this is just kind of going over what I said on the first slide, that balancing chemical equations is an outcome of law of conservation of mass. So keep in mind, if I give you the masses of the reactants, so I'm just making this up. Let's say I had 100 grams of calcium chloride and 200.23 grams of sodium sulfate. And let's say I produced 89 grams of sodium chloride, and I asked you, how much calcium sulfate did I make? Okay, you just have to make sure that the mass of the total reactants equals the mass of the total products. Combustion is a type of reaction you need to become familiar with pretty quickly. Combustion simply means burning. And you probably know in practical terms, when you burn something, it needs oxygen, right? Otherwise, the flame goes out if you smother it. And so one of the reactants for combustion or burning is always oxygen. That's important to remember. We get most of our man-made energy supply by combusting hydrocarbons. Okay, what is a hydrocarbon? Just kind of what it says, a compound that contains only hydrogen and carbon. Okay, this one happens to be methane. The technical name would be carbon tetrahydride. The products of combustion are always carbon dioxide and water. So combustion's an easy reaction to memorize. Oxygen's always a reactant. Carbon dioxide and water are always products. I'd like you to look at this reaction with a different perspective for a moment. If I gave you this formula and I said, does this reaction follow the law of conservation of mass? What would you say? I'm hoping that to find out, you would count the number of N types of each atom on both sides of the reaction and make sure they were equal. If you did so, you'd find that's not the case. On the reactant side, you have 1 carbon, 4 hydrogens, and 2 oxygen atoms. On the product side, you have 1 carbon, so that's balanced, same number of carbons. You have 2 hydrogens, okay? Remember the reactant side had 4, and you have 2 plus 1 or 3 oxygens. So it's not following the law of conservation of mass. This reaction needs to be balanced. In order to balance a reaction, you can only change coefficients. Coefficients is the large number in front of each molecule or atom. Okay, so A, B, C, D that I'm writing in now represent coefficients. That's all you can touch when you're balancing a reaction. You may not change any of the subscripts. They make the compound what it is. That's the identity of the compound. You can't mess with those. So if we look at models that represent the molecules instead of the symbols, it might be easier for you to see how this is balanced. So as the way the reaction was written in the last slide, we had one of everything. We had one CH4, one O2. See, each of these are oxygen. Carbon's in the middle, it's black, and each of the white things are hydrogen. Okay. And then carbon dioxide and water. So oxygen. Okay. So in the beginning we had one of each. So if you cover up these two guys down here, that's what we started with. Well, you can't balance by saying, I need one more oxygen on the reactant side, so let me just cut this oxygen molecule in half and take one of them. No, you can't do that. You have to keep the entire molecule as it exists. So then how do you get things balanced? All right, so we know we need more oxygen on the reactant side, and the only way to get that is to add oxygen molecules. So we have to add one whole oxygen molecule, which now gives us 4 oxygen atoms. One, 2, 3, 4 on the reactant side. So when we started, we had 1, 2, 3 oxygens. We can add another water molecule. So it's just kind of a pictorial. I'm not going to ask you to do this, but I just want you to kind of visualize in your head that by changing coefficients, you're adding whole nother molecules, not just part of them. You can tell I'm really emphasizing this point because this is about the 4th slide on it. So looking at this equation, if you combine hydrogen and oxygen with a little spark, you do get water. It's not balanced because you have 2 oxygen on the reactant side and only 1 on the product side. You can balance it by using these coefficients. You may not just change a subscript. Not allowed, because now you've created, which is not going to happen, H2O2, which is hydrogen peroxide. It's not water anymore. Okay, so only the coefficients can be changed. Here's a set of rules I use for balancing. I strongly suggest you commit them to memory. They have never failed me. If you have enough discipline to make yourself follow these rules in order, you will be able to balance anything, okay? So balance metals first, balance polyatomic ions second, and when you see a polyatomic ion, so let's say you have a carbonate group, balance it as a unit, not as individual carbon and oxygen atoms. So you would say, okay, I have one carbonate group on this side, so keep them together as a group. Then always save hydrogen for next to last to balance. It's a tough one to balance. And save oxygen till final, the very last thing you balance. Okay? Hydrogen next to last and oxygen last. Let's try to do it with this equation. Balance metals first. Do we have a metal? Yes, aluminum. We have 1 aluminum on the reactant side. We have 2 aluminum on the product side. I can only change coefficients, so I'm going to put a 2 in front of the aluminum on the reactant side. So now I have 2 aluminum on both sides. I have 2 bromine on the reactant side, but I have 6 bromine on the product side. How do I get 6 bromine on the reactant side? I'm going to put a coefficient of 3 in front of bromine. You always multiply coefficient times subscript to see how many total atoms you have. And now 3 times 2 is 6. So I have 6 bromine atoms on the reactant side. This reaction is balanced. Try to balance these on your own. They can be a little tricky, but give it a shot. You may remember a little bit from high school. At least give it a shot. Don't be hard on yourself if you're not able to do them. So put the video on pause now, and then when you're ready to compare your answers, turn it back on, and I'm going to work them out for you. All right, well, in the first reaction I've shown here, okay, there are no metals, so there goes that rule. There are no polyatomics, there goes that rule. Now remember I said to balance oxygen last and hydrogen next to last. So what does that leave us? That leaves us to start with carbon, okay? So I have 3 carbon atoms, 3 carbon atoms on the reactant side and 1 carbon atom on the product side. So I want to make the number of carbon atoms equal. So I'm going to put a 3 coefficient in front of this carbon dioxide, and now I have 3 carbon atoms on both sides. Then you're supposed to balance hydrogen next to last, so I'm going to look at hydrogen now. I have 8 hydrogen atoms on the reactant side and only 2 on the product side. So I need to make these 2 hydrogens equal to 8. How do I do so? I'm going to put a coefficient of 4 in front of the water molecule. 4 times 2 is 8. So I now have 8 hydrogens. All right, save oxygen till last. So now let's see how many oxygen we have on both sides. You have to be especially careful with combustion because you have 2 sources of oxygen on the product side. So from carbon dioxide, I have 3 times 2 or 6 oxygen atoms. From the water molecule, I have 4 times 1 or 4 more oxygen atoms. So I have a total of 10 oxygen atoms. You may hear my dogs in the background, sorry. 10 oxygen atoms on the product side. And I only have 2 oxygen atoms on the reactant side. How do I get 10 oxygen atoms on the reactant side? By putting a 5. So the answer, if you were to write the answer, there's 1 C3H8, 5 oxygen molecules, 3 carbon dioxide, and 4 water molecules. If you haven't tried the second reaction, give it a try now. Put the video on pause. Alrighty, so I'm going to balance metals first. Silver is a metal, so I'm going to put a 2 in front of the silver here so that I have 2 silvers on each side. Balance, there aren't any other metals, so balance polyatomics next. I have an SO4 or sulfate group on both sides, so I can balance them as a group rather than individual atoms. I have 1 sulfate group on the reactant side, and so far 1 sulfate group on the product side. So I'm going to leave those alone, they're already balanced. I'm supposed to save hydrogen and oxygen till last, so the only thing that's left besides that is the chlorine. So I have 1 chlorine on the reactant side, but I have 2 chlorine on the product side. So I need to put a 2 coefficient here so that I now have 2 chlorine on the reactant side. All that's left is hydrogen. Remember the oxygens in SO4 are already balanced, so just ignore them. How many hydrogen do I have on each side? I have 2 hydrogen on the reactant side and 2 on the product side. So the coefficients that balance this reaction are 1, 2, 2, 1. Balancing these reactions are more challenging than the ones on the previous page. So if you feel like you're getting it, please give these a shot. Go ahead and turn off the video, try it on your own, and then turn it back on and I will work them out for you. Alrighty. So for the first one up here, it's another combustion. I think combustions can be the trickiest to balance, honestly. I have a special little rule I use for combustions, and I call them the CHO rule. Balance carbon first, then hydrogen, then oxygen. CHO. All right, so carbon first. I'm going to put a 4 in front of carbon dioxide so that there are 4 carbons on both sides. Then I'm left with hydrogen and oxygen. I have 10 on the reactant side, only 2 on the product side. And now my dogs are drinking water. This is not a real professional one, sorry about that. So if I want 10 hydrogen on the product side, I'm going to put a coefficient of 5 in front of water. So now my carbon and hydrogen are balanced. I just need to check oxygen. I have 2 oxygen on the reactant side. Remember I said be careful counting oxygen in combustion reactions on the product side because you have 2 sources of oxygen. So we have 4 times 2 or 8 oxygen from CO2. And then we have 5 more from water. So I have a total of 13 oxygen. Listen very carefully. Now there's a trick for solving everything. How do I get 13, an odd number of oxygen, when oxygen is a diatomic? Okay, if I were to put a 6 in front of it, I would only have 12 oxygen. If I were to put a 7 in front of it, I would have 14 oxygen. So what do I do? Okay, so what you do is you multiply every coefficient you have so far by 2. So we start out with, we had a 1, assumed to be a 1 in front of C4H10. We are now going to put a 2. We're going to leave, this is the one we're trying to balance, so we're going to leave that blank for now. We're going to change the 4 in front of CO2 to an 8. I'm going to multiply every coefficient by 2. And change this 5 in front of water to 10. Lovely background noise. Now my dogs are eating. So now with that in mind, now you can put the 13 oxygen here and it'll be balanced. Let me show you why. Let's recount oxygen on the product side. Now we have 8 times 2. We have 16 oxygen. And 10 more, so 16 plus 10 is, I'm getting too messy here, 26 oxygen atoms on the product side. How many do we have on the reactant side? 13 times 2, 26. So that type of combustion where you end up with an odd number of oxygen atoms is one of the more difficult ones, but it's a level I expect you to be able to do if you want an A or B in the course, so you need to practice a bunch of balancing reactions. Let's look at the last one. We don't have any metals, we don't have any polyatomics, but we're going to save hydrogen and oxygen till last. So that means we're going to balance the boron first. I have 4 on the reactant side, 2 on the product side. So I'm going to put a 2 coefficient in front of the product side. So 2 times 2 is 4. Boron is now balanced. Then I'm going to balance hydrogen. I have 10 hydrogen on the reactant side and only 2 on the product side. So I'm going to put a 5 coefficient in front of the water. So I now have 5 times 2, or 10 hydrogen on the product side. All that's left is oxygen. Be careful, look at the product side. There are 2 sources of oxygen. I have 2 times 3, or 6 oxygen from the B2O3. and 5 more from the water. So I have a total of 11 oxygen on the reactant side. So I'm in the same type of situation as I was with the combustion reaction. How do I get an odd number of oxygen when I have O2? Follow what I told you before, multiply all the coefficients you have so far by 2, and then you can insert that 11. So it's assumed there's a 1 in front of the B4H10. We're now going to put a 2. We can insert the 11 here. We've got to change all the other coefficients, multiply them by 2. So instead of a 2 in front of B2O3, I'm going to put a 4. And instead of 5 in front of water, I'm going to put a 10. So the final balance coefficients are 2, 11, 4, and 10. And the final challenge for you is to put together the naming that we've learned and balancing reactions. Okay, this is all preparation for getting into actually understanding chemical reactions. So you should be able to take each of these names, turn them into a chemical formula, and then balance it. If you feel up to it, I would suggest you try it on your own first, turn the video off, and then I will work it for you. All right, so here goes. Sodium phosphate. Remember, it's ionic, it has a metal, so writing formula is a two-step process. Write the ions with their charges and then crisscross. So the formula for sodium phosphate is Na3PO4. All right, so now my dogs are going to play fight for you. We have another ionic compound, iron. The Roman numeral 3 tells you its charge. Oxide is simply oxygen from the periodic table, which always has a charge of -2. Crisscross, and I find the formula for iron 3 oxide, which is rust, by the way, is Fe2O3. Now to the product side. Sodium oxide. All of these are ionic. Sodium oxide, crisscross, Na2O, and the other product, iron 3 phosphate, iron +3 charge from the Roman numerals, phosphate has a -3 charge. I'm hoping at this point that you'll notice, since the cation and anion have equal but opposite charges, they combine in a 1-to-1 ratio to make FePO4. If you happen to not notice that and you crisscross these, that's fine, as long as you remember that ionic compounds, whenever possible, have to be simplified. I can divide both of these coefficients by 3 to give Fe1, of course, PO4, 1. Same thing. Alrighty, so what do we have? Bottom line, let me write out this equation. You're not quite done. You also have to balance it. So this is what you have so far from the naming, and now you always have to see if you need to change the coefficients to balance it. So we're going to start with metals, and we have 2 metals. So we have sodium and iron. So we're going to balance those first. There are 3 sodium on the reactant side and 2 on the product side. How do we get 3 and 2 to be equal? Multiply them by each other. That almost always works. So 3 times 2 is 6, so I'm going to make 6 sodium on both sides. So I'm going to put a 2 in front of here. 2 times 3 is, so I have 6 sodium on the reactant side. And I'm going to put a 3 besides sodium oxide, because 3 times 2 is also 6, and now I have 6 sodium on both sides. Then I'm going to balance the other metal, which is iron. I have 2 iron on the reactant side and only 1 Product side, thank goodness that's a little bit easier, so I just need to put a 2 coefficient on the product side, and now I have 2 ions on each side. All right, so balance polyatomics next. I have 1 polyatomic, and it's PO4, phosphate. Remember I said balance them as a group. Don't divide them into phosphorus and oxygen atoms. It's a lot more complicated. I have 2 phosphate groups on the reactant side. And I have, I'm so thankful I don't have to mess with it, 2 phosphate groups on the product side. Yay, they're already balanced. What do I have left to balance? The only thing I have left are the oxygens that are not part of PO4. Don't rebalance the oxygens in PO4. You've already balanced those. So I'm looking at balancing the oxygen that's in iron 3 oxide, rust, with the oxygen that's in sodium oxide. So we're assuming there's a 1. Anytime there's not a coefficient, you assume it's 1. So 1 times 3, so I have 3 oxygen atoms on the reactant side, and assume there's a subscript 1 there, 3 times 1, or 3 oxygen atoms on the product side. We are balanced. So the final coefficients that balance this reaction are 2, 1, 3, 2. It's probably clear to you, I hope, that you need to practice balancing an awful lot to get it. That's it for this video, though.